Hi everyone, I am Shubham Garg and welcome back to the lecture series of DSCH Software. So in today's video we are going to see how to make XNOR and XOR gate using CMOS logic. Okay, so here on my screen it is XNOR gate. So let us first see how the XNOR gate is functioning, and then we will see how to build the XNOR gate, and after that we will see how to build the XOR gate as well. So I will start the simulation. Just click on run simulation. And you can see in XNOR gate, when both the inputs are 0, the output is 1. When any of the input is 1, the output is 0. When both the inputs are 1, the output is again 1. Alright, and you see if I turn this on, that is 1, and I make this one as off, that is 0, then it is also 0. That is, whenever there is the same input on both of the terminals, then the output will be 1. Whenever there is a different input, the output will be 0. So this is how our XNOR gate works. So let us see how we develop this XNOR gate. Okay, so for that, let's see the truth table and the equation of XNOR gate. Okay, so we know XNOR gate is basically gives the output as A dot B plus A dot B whole complement. Alright, so this is the output of XNOR gate. Okay, let me just maximize this. Yeah, so this is the output for the XNOR gate. Now what happens here, like either we can make our XNOR gate like this, okay, but if you remember the conditions of the XNOR gate, you must know that there was one condition. There was a condition that the XNOR gate, there was a condition that any CMOS logic basically gives us the complementary function. Okay, complementary function. That is, every function which we get as the output is in the complemented form. That is, we do not get the output as A dot B, we get output as A dot B complement. Or we do not get the output as A plus B, we get the output as A plus B complement. So that means if we develop this A dot B plus A dot B whole complement, then we will be getting the output as A dot B plus A dot B whole complement and then again whole complement. This function is we are going to get as the output. Okay, if we try to make the XNOR gate using this equation. All right. So now what will happen to make it? It becomes XOR gate instead of XNOR. So then again to make it as the XNOR gate, we have to add another complement, that is another inverter. Okay, so that basically increases the number of inverters, and the number of transistors which we are using. So that's why we won't be using this function to make our XNOR gate. What we will do is we will create the XOR gate. Okay, and we will the function will be complementary for XOR if we try to create the XOR gate. So you can see here, this one is the equation for XOR. The below equation which I have written, that is A dot B bar plus A bar dot B. This function till this, it is for XOR. That is okay. Yeah, there can be confusion with this bar. Let me just erase this. Yeah. So now you can see this one is for XOR, that is A dot B bar plus A bar dot B. Okay, this is the function for XOR gate. However, when we will build the XOR gate, using CMOS logic, what will happen? We won't get this XOR function, we get the complementary function, that is, we get this thing. And complementary for XOR is the XNOR. So the function which we are getting as the output is the XNOR function. Alright, so you can see before we have to use two inverters to make this function XNOR, now we don't have to use any inverter because we already get the complementary function. And now when we need to make this function as XOR, okay, since this is XNOR, because we get the complementary function, when we have to make this XOR, we just take one complement. We just complement it one more time. That is, we add one inverter. So you can see, using only one inverter, we can get XOR, and with zero inverters, we are getting the XNOR. But here, for XOR, we need one inverter, and for XNOR, we need two inverters. Okay, so that's why we are going to use this equation. Let me just highlight this. So we will be using this equation to build our XNOR gate. Yeah, okay, XOR gate and XNOR gate we will be building using this. So I will just erase everything extra here, and will write the final equation. So here is our final equation, that is XNOR. Okay, XNOR, and the equation will be A dot B bar plus A bar dot B and whole complement. All right. So this will be our equation, and we just need to implement this function because we are getting complementary output, so we don't have to add any inverter. All right. So let us design our gate according to the equation. So let me delete this as well. Okay. So this is our final equation. Let me just highlight it. So this is our final equation. This is our final equation, and we will build the schematic using this equation. All right. So here is the truth table for XNOR gate. That is, whenever both the inputs are 0, the output is 1. Whenever both the inputs are 1, the output is 1. That is, for same input, output is 1. For different inputs, output is 0. Okay. So let us move towards DSCH, and I will create a new schematic. Okay, I am going to go to file, and then I will click new. Now one thing what we need to understand is that we have two inputs and one output, that is A and B are the inputs and Y is the output. So that's why we need two buttons, that is one for A and one for B. All right. So now we have two inputs, that is one for A and one for B. So I will also change the name for the input, and that is input A, and I am going to flip this B input, and I will change its name to B. Okay, and then we have one output. So we will use the LED later on. All right. So after that, you can see that in the two inputs in the equation, there is A dot B complement plus A complement dot B. All right, that is for ones in the first equation, that is in the first part of the equation, A dot B complement, the B is in the complemented form. All right, and in the second part, that is A complement dot B, A is in the complemented form. All right, so that means we need to use the inverter in the inputs as well. Okay, so now what we can do is we can either use the CMOS inverter, which we have made before. All right, but since that is not the main focus for us, so what we will do is we will use the inverter which is available in the library. Okay, so in the symbol library, you can see here, this is the symbol of inverter and it is present, and you can just drag and drop the inverter. So you can just drag and drop, and here is your inverter. Okay, similarly you can attach an inverter on B as well. Okay, I will just move it to some distance. So here is the inverter, and you can use your CMOS inverter as well, but since our focus is not on the inverter, we are focusing on the XOR gate, that's why we are using this inverter. Alright, and even in the later videos we will see how to make a symbol. So we will be making the symbol of our CMOS inverter, and we will be using that symbol instead of this as the inverter. Okay, so in that way our inverter won't be taking much space here. Alright, it will be only a symbol like this. So this is our A input, and this will be A complement output. This is B input, B complement output. Now when you see the equation, A dot B complement plus A complement dot B. Alright, so first there is dot between them, that is A and B complement will be in parallel. So we need two PMOS transistor. Yeah, so just drag and drop two PMOS transistor, and they should be in parallel, that is A and B complement. Alright, so just flip it. Yeah, so first of all let's connect the source and drains of the transistors, because these are in parallel. And now this input is connected to A, and the other one, this one, is connected to B complement. You can see from the equation, first is A dot B complement. Okay, so this input, yeah, this input is connected to A, and the other input is connected to B complement. So here is our B complement. You can see this input is connected to A, and this input is connected to B complement. Now if we see the next part of the equation, that is A complement dot B. That means again two transistors are in parallel, that is two PMOS in parallel, because we are making first pull up network first, and first input will be connected to A complement, other will be connected to the B complement. Okay, so again we have two PMOS, one here and other here. Alright, so we will flip this. Okay, you could also have copied this one as well, it's up to you. So here are again two PMOS, and these should be in parallel as well. And now here this PMOS is connected to A complement, and this PMOS is connected to B. Okay, you can see A complement dot B, and both of these have a plus sign between them, that is they must be connected in series. Alright, so these two are in parallel, the two transistors here are in parallel, the two transistors here are in parallel, and both the combination will be in series. So just use a wire and connect them in series. So this is our pull up network, and now we will add the supply. Okay, so this is our pull up network which is completed till now, and similarly we are going to make the pull down network, that will be consisting of the NMOS transistor. So first of all this is the wire for the output. Okay, so here is our output, so we will attach the LED here, and now we will make the pull down network. Okay, so for pull down network the rules are the opposite of the pull up network, that is if there is a dot, then the transistors will be in series. So we will have A and B complement in series. Okay, for the first part we have A and B complement in series. So you can see we need NMOS transistor here, so that is, let's say it is for A and this is for B complement. These two should be in series. Similarly A complement dot B should be in series because there is a dot between them. Okay, so I will just copy it and I will paste it here. Okay, let's flip it as well. So now we have A dot B complement and A complement dot B in series, and you can see there is a plus sign between them. So in the pull down network, both of these combination should be in parallel. Alright, so let us connect both these combination in parallel. So now both of these combinations are connected in parallel, and I will just add the ground here, and now we will just connect these towards the input. So first is A dot B complement. So one input should be connected to A, other should be connected to B complement. So let us take our wire, and here is this A. Okay, now this needs to be connected to B complement, that is here. All right. So I am going to use a wire. So here is our B complement. Similarly, the next part, A complement dot B. All right. So first one needs to be connected to A complement. So I will again use wire, and here is our A complement, and now second one needs to be connected to B. So here second is connected to B. So now this is our XNOR gate, and let us run the simulation to see if it is working fine or not. So let's run the simulation, and you can see when both the inputs are 0, the output is 1. When any of the input is 1, the output is 0. When both the inputs are 1, the output is 1 again. Okay, and you can see the other way around, that is if this is 1 and this is 0, the output is 0. That is on same inputs, output is 1. On different inputs, output is 0. Now let us see why this is happening. That is why XOR gate is functioning this way. Although if you are following my all the videos, then most probably you have already figured it out. Anyways, let's see how the logic is transferring. So you see when the input A is 0, what happens due to inverter, the output here we get is 1. Okay, so when we get 1, this PMOS become open circuited. Okay, so therefore no current flows here. However, the 1 flows through this wire as well, and whenever we are there here at this NMOS, okay, the NMOS is on, but no logic 0 flows because this NMOS is open circuited. Similarly, here this NMOS is open circuited, so no logic 0 flows. Okay, so now here B is also 0. So when we get the complemented output, here we get 1. Okay, so for 1, this PMOS is turned off, this is open circuited. All right, and similarly here this NMOS is on. Okay, so from here what is happening, since both of these are connected in parallel, thus from here because this PMOS there is input 0 and this PMOS in input 0 is short circuited. Thus what is happening, it is allowing logic 1, that is VDD, to pass through it because it is short circuited, and this logic 1 is passing here because the input A is 0. All right, so now this logic 1 passes through here, then comes here. Similarly, here the input B is 0, hence this is short circuited again, so the logic 1 passes from here towards the output. Okay, so this is how our XNOR gate is working. When you open any of the input, what is happening, due to 0 here, since this is A is 1, but due to this PMOS the complemented output it is 0, both of these are open circuited, hence no VDD flows. Whereas in the pull down network, when A is 1, this is short circuited. Okay, similarly when B complement is 1, this is also short circuited, hence from the ground logic 0 flows towards the output. So this is how the XNOR gate is working. And now this is our XNOR gate. Now if we want to make the XOR gate using XNOR gate, what we will do is we will just add an inverter. You can see, because we get the complemented function, we will just add an inverter to make the XOR gate. So let me just write the equation for XOR. Okay. However, the equation for XOR is only till here, that is a dot b plus a bar dot b. But we are since we have made this logic, we will get complemented function, and to make it XOR, we will add just one inverter. So this is our equation for XOR gate, and now we will add an inverter towards the output. Okay, so I will just extend the output here. You can just move the windows like this using arrow keys. Okay, so you can suit the workspace according to your need. Yeah, so now I am just going to extend the wire, and here I am going to add insert an inverter. So just go to add insert symbol and just select all files, because we have not made any symbol yet, but we will make inverter. We will make various symbol in upcoming videos. Okay, so just select inverter CMOS and click open. So here is our inverter. All right, so now we just need to connect this inverter towards the input, towards the output, and using the wire we will just connect this inverter towards the output. Okay, so now our output is connected towards the inverter, so it should start working like an XOR gate. All right, so now what will be the truth table for XOR gate? In XNOR, we are getting 1 for the same input and 0 on the different input. However, in the case of XOR, we will get the opposite. That is, let's say A, B and Y, 0, 0, 1, 1. 0, 1, 0, 1. Okay, so now before we were getting previously, okay, it is not scrolling up. Yeah, so anyway, we were getting 1 on the same inputs. Okay, so here we will get 0 on the same inputs and 1 on the different inputs. Okay, so this will be our truth table for XOR gates. Now let us see if our schematic is giving these results. So let us run the simulation, and you can see when both the inputs are 0, the output is 0, and when any of the input is 1, the output is 1. So this is how we have developed XOR and XNOR gate using DSCH. So now make sure to always save your schematic. This one is XOR CMOS. Okay, CMOS. Yeah, XOR CMOS. So we will just save it here so that we can use it in different programs. Okay, and we can create the symbol as well. Okay, there was some error. Anyway, it seems it was great. It was a good idea to save the schematic. Okay, so that's why you always save your schematic. You see, due to some error, the software stopped working. Anyway, you have learned the logic. That's how things are going to work using DSCH, and we have made the XOR and XNOR gate. So after that, in the next video or upcoming videos, we will see how to generate the symbol using for the schematics which we have developed so far. And later on, we will be using those symbols in our bigger programs. All right, when we will be making combinational circuit, flip-flops or something like that. So this is all for this video, guys. See you in the next video.